In this video, we're going to move on to talking about quotients. One thing you may have noticed about all the things that we did with products, in all of our examples, they involve functions that we could have expanded out before differentiating, and that would have avoided having to use the product rule at all. Now, of course, we're not quite at the point where I can give you problems where we absolutely have to use the product rule. We will definitely see some of those even starting in the next section, when we start talking about what we call the chain rule. And then when we get on to talking about things involving exponentials and logarithms, we definitely have to have it there as well. We won't have the luxury of being able to expand things out and not use the product rule. But for the moment, we don't have access to those functions unless we were to go try to use the limit definition anyways. However, this is definitely not the case with quotients. We have very simple functions, say something like f of x is equal to x over x minus 5. This is something we can't expand out. We definitely can't really do anything to simplify this and be able to differentiate it using our rules that we have up to this point. Unless we want to go back to the limit definition. We could differentiate this with the limit definition of the derivative. It'd just be kind of a lot of work. So how do quotients really behave? And what kind of rule do we have? Well, part of the formula is going to end up really similar to the product rule. It's what we call the quotient rule. The derivative of f of x divided by g of x. We're going to have the derivative of f, not times or divided by the derivative of g, but actually times g of x itself, minus f of x, not the derivative, but just f of x, times the derivative of g. And that is all going to be on top of g of x squared. Or you might put that in parentheses. So basically, we take the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. Note that the numerator does kind of look like the product rule, but it does have this negative sign in it, this minus sign. The way I like to remember stuff here is that the minus sign is always on the term that has the derivative of the bottom. So anytime you have something from the bottom that's being differentiated, you end up with a minus sign there to go with it. Now, unlike the product rule, I'm not going to give a proof of this at this point. If you do want to, you can look at the way the book does it. It writes out the proof in detail, and it goes fairly similar to how the product rule goes. It just has a lot more steps or a lot more algebra things to it. It takes up pretty much the entire page to write out. But I don't really find that proof incredibly enlightening. In fact, I'm going to show you a proof in the next section of the quotient rule using the rule that we're going to get there, the chain rule that we get from the next section, that I find a lot more enlightening. That sheds a lot more light on why this turns out the way it does, why it looks so close to the product rule, but has certain differences in it. But for the moment, we're just going to take this formula, and we're going to work with it. So let's start working on some problems. I'm going to start with problem 11. Or they call this h. h of x is x divided by x minus 5. Might look a little familiar. This was the example function that said we needed the quotient rule for. So we're going to go ahead and differentiate this using the quotient rule. So the derivative, I take the derivative of the top. The derivative of x is 1 times the bottom not the derivative of the bottom, just whatever's already there on the bottom, then minus the top as it already is, the x that we have, times the derivative of the bottom. Derivative of x minus 5 is 1. And then I'm going to divide by whatever's on the bottom, this x minus 5 squared. I'm going to go ahead and simplify this because it does simplify pretty well. The ones here you might as well leave out. So we have x minus 5 minus x, and then this x actually cancels with that x. So we still have the minus 5 on top, and of course we saw the x minus 5 squared on the bottom. So the derivative of this function is this function. Nice and simple. Let's look at problem 12. It's a pretty similar kind of problem. This time the top is x squared, and the bottom is x plus 3. We still follow our quotient rule. So we take the derivative of the top. So this x squared becomes a 2x. I'm going to take that derivative times whatever's already on the bottom. So x plus 3. Minus the top. So this x squared. Times the derivative of the bottom. So the x plus 3 derivative is 1. And of course we have the whatever's on the bottom already, this x plus 3, but squared. Of course, we can simplify this one a little bit as well. This 2x we can distribute to the x and the 3. That becomes a 2x squared plus 6x. But we already have the minus x squared on there. If we combine like terms, we have the 2x squared minus x squared. We'll just give an x squared. We still have the 6x. And we still have the x plus 3 squared. So without having to use the limit definition at all, we can now differentiate products pretty easily. Moving right along, let's look at problem 20. Problem 20 says f of x is 5 minus 1 over x squared over x plus 2. There's actually a couple things that we can do here. For one, we could actually just go ahead and use the quotient rule immediately. But in that case, we would go ahead and replace the 1 over x squared with just x to the negative 2 power. And we have to use the power rule for that part. Let's go ahead and actually do that. So the derivative of this, we have the derivative of the top. Well, derivative of 5 is 0. Derivative of negative x to the negative 2, we need to bring down that negative 2, combine with the negative that's already there. So we have a negative times negative 2, which is a positive 2. But now when we reduce the power by 1, the negative 2 becomes a negative 3. We're going to take that and we're going to multiply it by what's on the bottom. We're going to multiply that by x plus 2. Now we subtract, we leave the top alone this time. And now we're going to differentiate the bottom. The x plus 2, when we differentiate it, we get a 1. Of course, then we divide by what's on the bottom squared. And we have a derivative. That's the derivative of the function. We could actually go ahead and simplify it if we wanted to. I'm not going to do it for this one. Instead, what I'm going to do is actually take a look at what the book is really expecting us to do. The book wants us to rewrite this function without having a fraction on top first. Instead of turning it into a negative power, what they want you to do is a little bit of algebra to change this into a slightly different function. I mean, it's the same function, just a different form. So what they basically want us to say, take this 5 minus 1 over x squared over x plus 2, and to get rid of the x squared on the bottom of this fraction that's on top, they want us to multiply the top and bottom by x squared. So when we multiply this top by x squared, of course the 5 becomes a 5x squared. The negative 1 over x squared times x squared just turns into negative 1. On the bottom, we still have to multiply by x squared just to not change the function. We need to multiply on top and bottom. So this x becomes an x cubed, and the plus 2 becomes a plus 2x squared. So now we don't have any negative exponents, we don't have any fractions inside of fractions, and we can use the quotient rule on this function, or this form of the function instead. So when we differentiate this time, we take the derivative of the top. So 5x squared becomes a 10x. The negative 1 becomes a 0. We take that times what we have on the bottom. So the x cubed plus 2x squared. We subtract what we already had on top, 5x squared minus 1. And now we multiply that by the derivative of the bottom. X cubed becomes a 3x squared. X squared becomes a 2x, which multiplied by 2 gives us a 4x. Finally, we get to divide by whatever was on the bottom squared. So we have an x cubed, should look more like a 3, x cubed plus 2x squared, then squared. So that is another form of the derivative of this function. And if you want, you could do some algebra to show that these actually give us the same result. The second one definitely looks more complicated, but it also doesn't have any negative exponents. So if you want to avoid negative exponents, maybe that'd be what you want to do. But the online homework is going to accept either or. They should accept either one of these. And on an exam, I would definitely take either method, because these are really the same. They're both actually derivatives of the same function. They're the same thing, just written in a different form. So whichever method you prefer here is up to you. Next up is problem 21. Here we have f of x is equal to x cubed plus 6x divided by 3. So we have another fraction, but before we jump immediately into using the quotient rule, notice that our denominator here is a constant. Because of that, we can actually use the multiple rule instead. If we instead write this function as 1/3 times x cubed plus 6x, this is actually similar to one of the problems that we had in the last video, when we were talking about the product rule. We don't have to differentiate as a product or as a quotient. Instead, we just take 1/3 times the derivative of what we have here. So the derivative of this is 1/3 times the derivative of x cubed plus 6x. The derivative of that is 3x squared, because we're using the power rule for x cubed. Then plus 6, because the x becomes a 1. Of course, in this particular case, we can actually simplify it, because everything has a 3 in it. We can cancel out with that 1/3. 3x squared divided by 3 is x squared, and 6 divided by 3 is 2. So the derivative is x squared plus 2. Note, however, that this only works so nicely because the constant is on the bottom. If we look at a very similar function, say g of x, which is just this upside down, we put 3 over x cubed plus 6x, we can't do that anymore. This is not just a constant times some polynomial. we actually do need to use the quotient rule in this one. Of course, the quotient rule is actually a little simpler than it might otherwise seem, because when we differentiate the top, we do get a 0. But remembering that as a separate rule actually is probably not so useful. So I'm going to take the derivative of the top, that's a 0, times what we have on the bottom, minus the top, which is just the 3 that we already have there, times the derivative of the bottom. Derivative of the bottom, well, actually, we already saw that what that was. It's 3x squared plus 6. And of course, on the bottom, we have the original bottom, the x cubed plus 6x, but now it's squared. Of course, this part here is just a 0. It might as well not be there. That's the advantage of having a constant on top. And then here, let's go ahead and I'm going to move the negative out in front, but I'm going to go ahead and distribute the 3. So 3x squared becomes a 9x squared, and 3 times 6 becomes an 18. That's probably how I would write that one. But unless you use the chain rule that we're going to talk about in the next section, this is pretty much the only way to deal with this function. And whether or not the chain rule or the quotient rule is the better one to use here is maybe a little debatable. Let's look at one more example. Problem 44. Here we have a function f of x, which is x plus 1 times 2x minus 7, and then divided by 2x plus 1. So here we have a product and a quotient. We are actually able to use both rules in tandem. And in fact, they really do combine pretty well. I mean, it's mostly just because products and quotients are really very well tied to each other. But it might be a little surprising how well they actually do work together. Recall when we multiplied 3 functions together and differentiated, all we had to do was differentiate each factor separately and leave the others alone. Here we can pretty much do the exact same thing for the numerator. Just keeping in mind that when we deal with the term that involves the derivative at the bottom, we need a minus sign. So the derivative of this, we take the x plus 1, the 2x minus 7, and the 2x plus 1. I'll differentiate the first of those, the x plus 1. That becomes a 1. That will be multiplied by the other two as they already were. Now I move on to the 2x minus 7. I'm going to differentiate that. In fact, I'm going to go ahead and do what I did last time. And I'm going to highlight the ones that are actually differentiated. So this time, I'm going to leave the x plus 1 alone. But I'm going to differentiate the 2x minus 7. Derivative of that is actually a 2, because we have a 2 in front of the x. And I'm going to leave the 2x plus 1 alone. Finally, I'm going to leave the x plus 1 and the 2x minus 7 alone. I'm going to differentiate the 2x plus 1. That will give us a 2. And because this did come from the denominator, it's from the bottom, we need to remember that we have a minus sign here. But then we also, from our quotient rule, we'd have to divide all of this by what was on the bottom squared. And that's our answer. I mean, we could simplify it if we wanted to, but we don't have to. We can actually even take this a little bit further. Let's say we have an even more complicated function. I'm going to call it g of x, where I'm going to essentially take f of x and I'm going to put in some more factors. So we have x plus 1 and 2x minus 7 on top, but we also have another x plus 2 factor. On the bottom, instead of just 2x plus 1, I'm also going to have a 3x plus 1. And I'm going to differentiate this function. Remember, now I have 5 different terms, or sorry, 5 different factors, I should say. We have all these different factors, and I'm going to differentiate each one of those separately while leaving all the other factors alone. And then anytime I use a factor from the bottom and differentiate it, I'm going to incorporate a minus sign like I did here. So we have a derivative for this. So first, I'm going to differentiate x plus 1. That becomes a 1. But then everything else is the same. Now I'm going to leave the x plus 1 alone. I'm going to differentiate the 2x minus 7. That becomes a 2, just like it did up here. And then I leave all the other factors alone. Gonna run myself out of space, but oh well. I'm just gonna move down here. Next, I'm going to differentiate the x plus 2. That's going to become a 1, but everything else is going to stay the same. My fourth factor is the 2x plus 1. I'm going to differentiate that and get a 2. But since I am dealing with the factor from the bottom, I'm going to have to put a minus sign. So I have a minus. We have x plus 1, 2x minus 7, x plus 2, all the same factors from the top. But I've differentiated the 2x plus 1 to get a 2. And I still have the 3x plus 1. And finally, I have the 3x plus 1. Again, since it's coming from the bottom, I will need to introduce a minus sign. But I leave all the other factors alone. And the derivative of 3x plus 1, when I differentiate it, of course, it becomes a 3. Because the 1 goes away, and the x becomes a 1. But of course, remember, we are dealing with a quotient here. So all of this, all 5 of these terms, are over what we have on the bottom squared. When I square the bottom, I can just square each of these factors separately. So 2x plus 1 squared times 3x plus 1 squared. Just don't expect me to expand out that numerator. That would take quite a long time. But the point here is that our product and quotient rules do allow us to quickly and easily get to these derivatives without having to go through any limit definitions. And potentially without having to do any sort of expansions. It just depends on what you need the derivatives for. If all you need to do was find the slope of a tangent line, you could go ahead and plug in whatever value of x you wanted into this formula. That would just involve plugging stuff into a calculator, and you get your answer. If you wanted to do some sort of stuff with like optimization, like we will in chapter 3, this would be a lot more complicated to do. But that's more of a nature of the fact that this does have a complicated derivative, and less to do with the fact that what the form of the quotient rule is. But I'm going to go ahead and leave this here. Don't expect to have anything like this particular G. I had to make that up for myself. The book even only has like a couple problems that are even on the level of the 44. I think, 43 and 44 and 53 and 54 are like that. but nothing else comes even anywhere close. It's usually just the quotient of two polynomials. So we're not getting super complicated with this. It doesn't really help. It doesn't really illustrate things too much to go overboard with them. But I just wanted to show you what was a possibility. So hopefully you've got an idea of how the quotient rule works, and you can go ahead and start differentiating functions. Remember to do a bunch of problems. Work these things through until you have these firmly ingrained in your mind. Because we are going to be using these throughout the rest of the course. In the next section, we will introduce our last rule for differentiation, or at least the last general rule. We will have rules for how to differentiate an exponential or logarithm later on, but those are more specific functions and less general rules for dealing with combining functions like we had for products, sums, quotients, and all that. We will have what we call the chain rule. And at that point, we'll pretty much be able to differentiate any function we can talk about. Any function whose component pieces we've already seen how to work with. So I'll see you there.